Hi all. Today we see a paper titled Gradients Are Not All You Need from Google research team and Radbourne University. So what this paper says that there are some recent successful applications of deep learning techniques in various systems. The reason behind is making the deep learning models to become a differentiable and use gradient based optimization utilizing the training data to train those models end to end. So this setup, which has been successfully done in deep learning, has been applied in various other tasks like simulating rigid body physics, graphics, molecular dynamics, and setting up different optimization procedures. But we have to be more cautious while setting up this because this gradient based optimization is a iterative technique, and this can be considered to be as an iterative differentiable systems, and there are large chances that these systems are being chaotic in nature. So before we go through this paper, uh, we have some basic assumption that we understand what does mean by dynamics, how that dynamics can be modeled as a dynamical systems, and what does mean by linear dynamical systems and nonlinear dynamical systems. What does mean by stability analysis of the dynamical systems, stability analysis of a nonlinear dynamical system, what is fixed equilibrium states, and what is chaotic system. Chaotic system is nothing but something, it's a dynamical system which has very, it's a deterministic system which has very high sensitivity to the initial conditions. So more details about what does mean by nonlinear dynamical systems, what are the stability analysis, existence, uniqueness theorems, and how do we analyze linear dynamical stability analysis of a linear dynamical system, stability analysis of a nonlinear dynamical systems, and what does mean by chaotic system, strange attractors, factors, all will be covered in a separate video lectures based on the book from Stephen Strogatz. And this is a book about that. Hope we will have some small descriptions about this book in later of this videos. So this second section, what does it says that, for example, we have an iterative systems by equations one. So this systems keeps evolving and updating the state vector sk plus one, and whether this system will blow up or the solutions will converge or stays within the limit, or it explodes based on the property of the linear operator a. So it's a time, it's a time dependent system because the linear are non-autonomous because the a changes with respect to different iterations. So the property of the a at that time step k will determine whether the system will be stable or unstable. So this property of the system is based on the eigenvalues of A, especially the largest eigenvalue of A. If the largest eigenvalue of A is seems greater than 1, the system will explode. If it is less than 1, it will try to converge to an fixed equilibrium solutions. Similarly, if we go for non-linear systems, we linearize around some interested point and see whether around that interested point whether that linearized systems, that a is from the Jacobian matrix, that linear system will converge or it diverge based upon the eigenvalues of the Jacobian systems. So coming to the deep learning architecture, we have loss function similar to a setup of equation 3, and while we are trying to do an optimization based on gradient techniques, we try to obtain a gradient of the loss functions, and the computer the gradient of loss functions involve equations 4 5 6 and keeps going on. And finally we have the total loss functions by equations 8, where we have a product of Jacobian matrices ds by dsi minus 1. So these Jacobian matrices will determine and update the gradient vector, and if those product of the Jacobian matrices has to be a stable operator, then these loss functions, the then the iterative steps of the gradient optimization will converge to a fixed equilibrium, else it will diverge away. So this Jacobian matrices eigenvalues will determine whether this iterative process of optimization will converge or will diverge. So that is the main crux of this paper. But how does this related to chaos? We'll see at this end of this paper, and there are some misconception of what is severe nonlinearity and what is chaotic systems in defining the way how this Jacobian matrices are diverging or converging. So these things, another way to make the system to become stable is introducing the randomness in the solution procedure, like stochasticity. So this randomness will give you some kind of an averaging process, which will give some smoothened way to compute the gradient, and that this averaging techniques makes the system to become well behaved, even though that individual trajectories are not. Especially it's applied to some kind of when you're applying to the recurrent neural network with loss functions in deep learning. This kind of averaging techniques will helpful making the system not to diverge far away. So where are these iterative systems kind of procedures being applied today, or somewhere related to rigid body physics? We need to make some finding the optimal parameters in the mathematical models of the rigid body physics. We utilize this optimization procedure. There is a large possibility for the optimization procedure to become chaotic systems, sensitivity to initial conditions, and can be diverge away, making these Jacobian matrices to become explode. So this is one kind of where it's been tried. This deep learning techniques in rigid body physics, and recently there were a paper called learning and optimizer, parameterizing and optimizers, and learning those parameters of the optimization through standard gradient based techniques. In those settings also there is a possibility for this kind of things scenarios to happen, where the Jacobian matrix or gradients can become explode, and molecular dynamics the same like as like rigid body physics. There are some simulations where we need the parameters has to be optimized, and again all these things are very well related connected to computing the gradient based optimization. We need to compute the Jacobian matrix, and it involves in updating the gradient, updating the parameters. It involves a gradient of the loss function. That gradient of the loss function involves the products of Jacobians, and the properties of the Jacobians mainly related to the eigenvalues will determine the process to be explode or converge. So what if these scenarios, if the iterative system is very sensitivity to the initial parameters, and there are large chances for the gradients to become explode, or the iterative process to become diverge, what are the things possibilities can be done has been recommended by this paper. One is to make the system to become well behaved, like for example in deep learning, recurrent neural networks have some vanishing or exploding gradient problems. So to address this, there are so many changes have happened during the earlier years. One is proper initializations. So the initialization has to be done in quite in a logical way, so that while propagating those parameters through the optimizations, those parameters try to converge to reasonable results. Another thing is to avoid those kind of exploding Jacobians. They change some recurrent structures. Instead of using a vanilla RNN, they use a different architecture called LSTM or GRU. Similarly, in rigid body physics, to avoid this severe ill condition nonlinearities in the systems, we try to smoothen out those factors like jump discontinuities are try to be avoided. So other things like, what are the other things is related to the deep learning things that what they have been achieved. That back propagations is in time when only when this happened, the explosion happened only after a specific number of time steps. So stepping number of iterative steps. So what does mean by is we propagate, we truncate those back propagation all from the final step to the initial steps. They propagate only through a fixed number of steps. Now, although this computed gradient is biased, but it doesn't involve in exploding or vanishing gradient problems. Another thing is gradient clipping between minus max to min to max value. When this exceeded, we try to clip it, and all again this gradient is biased and will not sometimes give you an optimal solutions. So other techniques what they have mentioned is all related to, as mentioned earlier, related to the averaging process. So this stochastic averaging process will give us a stable operations, although the initial trajectories are not stable enough. So the final discussion is about that. They says that this optimization based upon this gradient is an iterative differential system which can become a chaotic systems for certain number of reasons, and especially in deep learning, this has been avoided by over parameterizations. But this over parameterization leads to computational bottleneck in propagation because it requires large memory and then the forward propagations. So what the author finally tried to say is it is not straightforward to use this gradient based optimization in although success has happened in deep learning. So this gradient based optimization has to be taken and should be properly utilized, considering this as a differentiable system is carrying. I deeply have a doubt whether this author wants to say is this a chaotic system or a deeply sensitivity of the nonlinear systems, because there are certain aspect that has to be understood related to the what this paper tries to say about. So this paper tries to say about phenomena called nonlinear phenomena and chaotic phenomena. So there are some. This book is beautifully written by Professor Steven Strogatz, and later I'm planning to conduct some series of video. Although there are some more videos from the author itself, but I'm trying to cover this book in a very in a briefly and condensed manner. So this has some says about what is chaos, what is fractals, what does mean by dynamics, how those dynamics evolve from Newton to Poincaré, and what is meant by dynamical system, what are the orders of dynamical system exist in this world, some of the examples, and what does mean to understand this dynamical system in one dimensional things, what is meant by equilibrium, what is meant by stability, and how to understand the stability analysis in a linear system, what does mean by bifurcations, when we changing to the parameter, how the stability becomes instability or instability becomes stability. All those things have covered beautifully in this paper, and I have read so many other books, but this book is exceptionally very well written, and it can be read like as reading a novel in chaos and linear phenomena. And coming to the two-dimensional flows, it says about the very important crux is linear systems. How what does mean by classification of linear system? What are the properties of the matrix, and how the properties of matrix can be analyzed to analyze this linear system, especially non-autonomous linear system. What is mean by phase plane? How does phase plane portrait happen? And how do we study this using this phase plane a geometrical way of understanding the dynamical system, what is meant by limit cycles, again it is related to the equilibrium conditions. And finally they says about what does mean by chaos, and they gave some beautiful definitions about chaos through the introductions of Lorentz equations. What does mean by how this Lorentz equations are derived, and they give some brief history about how these equations are being derived, and Lorentz map, and strange attractor. And again that what we saw here is one and that gradient based iterative system is nothing but an iterative map. How does those iterative map becomes a chaotic in nature through an example called logistic map. Then finally, how those equilibrium solutions are appear to be as a fractals. What does mean by strange attractors, and how does this connected to chaos and fractal systems. So hopefully this book you can read yourself, but I will try to cover briefly in one or two videos the whole book in a condensed matter. So hopefully we'll see you in some other interesting topics in the next video. Thank you.